You ever stop and wonder why you can bend a metal spoon, but if you tried that with a piece of charcoal, it would just shatter? I mean, the difference seems pretty obvious, right? But the real reason, the deep down secret, is hidden inside their atoms. So let's dive in and uncover exactly what's going on at the atomic level.
I mean, just look at them side by side. The differences are just striking. You've got your shiny metals like a spoon, and then your dull nonmetals like a piece of charcoal. We see this stuff every single day. You know that metals feel heavy, dense, and solid, while nonmetals often feel way lighter, and sometimes they're super brittle.
But here's the thing. This is way more than just skin deep. All those things we can see and feel, they're really just clues, symptoms of a huge difference at the most fundamental level. So what is it? What's the secret ingredient that actually makes a metal a metal?
Okay, so to really get to the bottom of this, we need to be super clear on what we're actually talking about. Let's officially introduce the two main players here, metals and nonmetals.
All right, first up, metals. Now, if you think back to the periodic table, these are the guys you'll find all over the left side and right in the middle. The textbook definition, they're shiny and they're fantastic at conducting heat and electricity. No surprise there.
And then you've got their counterparts, the nonmetals. They hang out mostly on the upper right-hand side of the periodic table. And, well, they're pretty much the exact opposite. They're poor conductors of heat, poor conductors of electricity. On paper, it all seems pretty black and white, right?
Okay, so now let's put them head to head. Let's really see how their properties stack up against each other. And this is where things get really interesting. And would you look at that? It's like they're almost perfect mirror images of each other. Metals, they tend to have really high melting points, high density. Nonmetals, the opposite. But the one I really want you to focus on, the most important one for our story, is that last one, malleability. Metals can be bent, they can be shaped. Nonmetals, they're brittle, they just shatter. And that is a huge clue.
But of course, in science, there are always some fun exceptions to the rules. Take mercury, for example. It's a metal, for sure, but it's a liquid at room temperature. Weird, right? And then there's graphite, you know the stuff in pencils? That's a form of carbon, a nonmetal, but it actually conducts electricity pretty well. These exceptions are awesome because they tell us our simple rules don't cover the whole story.
And all of this brings us right to the big question, the really crucial point. We know what the differences are, we can see them, but why? Why can metals conduct electricity so well? Why can you hammer a chunk of gold into a super thin sheet and it doesn't just fall apart? The answer, my friends, is not something you can see with your eyes.
To find that answer, we have to zoom in, way in. We've got to leave the world of spoons and charcoal behind and travel down into the microscopic world of the atom itself. And here it is. This is the secret. The whole explanation for every single one of those properties we talked about, the shininess, the conductivity, the malleability, it all comes down to one single thing, the completely unique way that metal atoms are bonded together.
And this special type of bond has a great name that honestly describes it perfectly. It's called the metallic bond, and its secret sauce is something we call a sea of electrons.
Okay, so before we can build our metal, we have to get our heads around this key idea, delocalized electrons. It's a fancy term, but here's what it means. In most chemical bonds, electrons are stuck, tied to one or maybe two atoms. But not these guys. Delocalized electrons are like free agents. They don't belong to any one atom. They are totally free to just roam around the entire structure.
So, let's picture how this whole thing comes together. Step 1, you start with a bunch of regular, neutral metal atoms. Step 2, the outermost electrons on each atom basically say, see ya, and leave their home atom. And step 3, what you're left with is this neat, orderly grid of positive metal ions just sitting there in a giant shared sea of all those electrons that just left. And that structure is what we call a metallic lattice.
So what's the glue holding this whole thing together? Well, that's the metallic bond itself. It's this really strong electrostatic attraction, opposites attract, between all those positive metal ions and that free-flowing sea of negative electrons swirling all around them. Think of it this way. The ions are locked in place, but that sea of electrons is completely fluid.
Okay, so we've got our model, positive ions floating in a sea of electrons. Now for the big payoff. This is where it all clicks into place. Let's connect this tiny atomic structure back to all those big properties we saw at the beginning. So, let's start with malleability. Why is it that you can hammer on a piece of metal, change its shape, and it doesn't shatter into a million pieces? How does our sea of electrons model explain that? Well, it's pretty cool. When you apply a force, like with a hammer, the layers of those positive ions can literally slide right over each other.
And the reason the whole thing doesn't break is because that fluid sea of electrons just flows right along with them. It acts like this amazing, flexible glue that holds everything together no matter what new shape it takes.
All right, so that explains why metals are bendy. But what about the other big one, conductivity? Why are metals so incredibly good at letting electricity flow right through them?
Yep, you guessed it. It's all because of those free-moving electrons again. When you apply a voltage across a piece of metal, it's like you're giving a giant push to that entire sea of electrons. And since they're free to move, they just flow. They travel through the lattice, carrying their charge with them. And what is a flow of charge? Well, that's literally the definition of an electric current.
So you see, this one unique idea, the metallic bond, explains pretty much everything about metals. But, it's always helpful to see where this fits into the bigger picture of how atoms hold together in general. So let's zoom back out for a second.
So here are the 4 main ways atoms bond. You've got ionic bonding, where electrons are basically stolen from one atom by another. Then there's covalent bonding, where electrons are shared nicely between a couple of atoms. But then look over at metallic bonding. It is the only one where the electrons are totally delocalized, completely free to move everywhere. That right there is its superpower.
Now, here's something that's really important to remember. Any scientific model we use, including the pictures we've been looking at, is really just a simplification. As this quote points out, our neat, static diagrams don't show the reality that those delocalized electrons are actually in constant, chaotic, frantic motion. So yeah, models are incredibly useful, but they never quite capture the full, messy reality.
And that really leaves us with a final big thought. We just used a pretty simple model, this idea of a sea of electrons, to unlock the secret of why metals are the way they are. It explains why copper wires can power your phone and why steel beams can hold up giant skyscrapers. But if even our best, most useful models are just simplifications, it really makes you wonder, doesn't it? What other incredible, hidden complexities are just waiting to be discovered inside all the ordinary materials that are sitting all around you right now?